Hello everyone and welcome to the Maths of Collisions session, which will include detecting collisions with circles and rectangles and what happens after a collision. So we will be looking into mathematical model of reflections. To detect collisions, we first of all have to consider a mathematical model of a circle. A circle can be quite funnily considered a extension of a point. So it's a point with a radius, okay? And if you think about it, if you have a circle with a radius of 0, it's indeed a point, okay? So mathematical definition of a circle is a set of points at the equal distance from a center, okay? This equal distance is called a radius. And the equation of a circle with the center at point 0, 0 is something that you may be familiar with. If we have a coordinate system with the center of this circle, the center of the circle is in the center of the coordinate system, then the formula for the circle is x squared plus y squared equals r squared. And it's quite obvious if you think about it, because if you have any point at the edge of the circle, so within the circle, please remember, circle is considered, just the edge, okay? Circle is empty inside, okay? If you want to think about a shape which is not empty, this will be a disk, okay? So there is a difference between a disk and a circle. We're talking about circle. So any points on the circle will be here. Its coordinates are x and y, and together with radius, they produce a right triangle. Okay, so this formula for the circle is just a consequence of Pythagorean theorem. Okay, x squared plus y squared equals r squared, because r is our hypotenuse. Okay, but we also have another interesting equation of a circle. Again, this is a circle with the center at the point 0, 0. It's quite an important formula, because it's most usually used to draw circles in computer graphics. The problem with this formula is with iteration, okay? R is a constant. If you create a circle which has a constant radius, it's just a number. But then the question is whether you should iterate x's and calculate y's, or you should iterate y's and iterate x's. Sorry, and calculate x's. The problem is that if you would iterate from 0 to radius along the x-axis, you could use this formula, which would be y equals square root of r squared minus x squared, to produce this point, this point, this point, this point, this point, and so on. But if you just imagine computer implementation of such a circle, you would end up with a very small density of points here, okay? Because a small difference in the value of x would produce a huge difference in the value of y. And this is why in the computer graphics we prefer a parametric equation of a circle, in which we iterate angle rather than a coordinate. And for any given angle alpha, which is shown here, we can find x as r cosine alpha and y as r sine alpha. So sorry, we still come back to trigonometry, but simple SOHCAHTOA is everywhere in computer graphics, and you will need SOHCAHTOA even to draw a circle on the screen. Don't worry too much about it. Most libraries will have a ready-to-use function to draw circles, but if you ever would need to draw a circle by yourself, this is the preferred option. You can iterate alpha from 0 to 360 degrees, so from 0 to 2 pi radians, and you will get the entire circle. So that's about drawing circles. It's a little bit off topic. I'm so happy Vlad has just made my day by typing in my chat, I love trigonometry. So I do as well, absolutely. And we will now follow on to a topic which is more directly connected to detecting collisions, and this is distance of a point from a circle. Okay, so a situation is like this. We have a circle. We know the center point of the circle, and of course we know the radius. Radius is r. And we have another point. Let's say it's outside the circle. It can be inside, but on this diagram it happens to be outside. And we need to find the distance between this point and the circle. Of course, there are two ways of finding this distance, and quite natural we'll be measuring distance from the center. Okay, this is something we just used in the rocket science exercise when we needed a distance from the rocket to the Earth and to the moon. Both Earth and the moon in a 2D game were represented by disks or circles, okay? But because this was universal gravity, so we really needed distance to the center of the Earth and center of the moon. And this is the formula for the distance measured from the center. And it's really as easy as it is. So you take P, it's just coordinates of P, you don't have to worry about it. Coordinates of P minus coordinates of the center of the circle. You should know by now that you can add coordinates, you can subtract coordinates. There is not a problem because coordinates can be represented as vectors, and operation of addition and subtraction of vectors is well defined. So we know what it means. Coordinate of P minus coordinate of P0. And you should also know that by doing this subtraction, we actually create a displacement vector, which is shown here as this blue vector. Okay, so this is displacement, and these vertical lines just say we are interested in the magnitude of displacement. Okay, magnitude of a displacement vector is a distance between 2 points, and in this case, it's a distance of the point from the center of a circle. But what if we really want this distance? Okay, the distance between the point and the surface of the circle. So this is the distance measured from the closest point on the perimeter of the circle, and the formula is very similar, but we have to add, not add, of course, subtract the radius. Okay, if we have all this distance here and we subtract the radius, what we are left with is just this distance here. Okay, just imagine ISS, International Space Station, and its distance from the center of the Earth is quite a long one. Okay, it will be around 7,000 kilometers, but most of this is the radius of the Earth. Okay, the radius of the Earth is much more than 6,000 kilometers. Okay, and the ISS is just 400 kilometers away from the surface of the Earth. So for ISS, the difference between distance measured from the center of the circle and from the perimeter of the circle would be huge. Okay, and this final one would be 400 kilometers. But you know what? If the commander of ISS needs to check if he crashed the Earth or he's still orbiting, okay, he will be much more interested in the second value, because the second value is just the altitude of the station above the Earth. And the only thing that he has to care about is that he has some space between the station and the surface of the Earth. This number is useless unless you know the radius of the Earth, okay? But this is very, very important. If the distance from the ISS to the closest point on the perimeter of the Earth is 0 or a negative number, this means that ISS crashed into the Earth. A catastrophe, okay? Hopefully it's still 400 kilometers or something like that. But why is it at all interesting for us? Because this formula is directly the formula for point-circle collision. Okay, so to find out if you have a collision between a point and a circle, you have to calculate this thing and check if it is less or equal to 0. If it is less or equal to 0, you have the condition of collision. If it is further, if it is greater than 0, there is no collision. Okay. Next thing, distance between two circles. Okay, what I said in the very beginning, circle can be considered an expansion of a point. Okay, so if we have a formula to find the distance between a point and a circle, of course, this is the distance between the circles measured between the centers. Okay, P1 minus P0. Okay, magnitude of this vector. But to find the distance measured between two perimeters, you just need to subtract both radiuses. So it's the distance between the centers minus R0 minus R1. R0 is the radius of this bigger circle. R1 is the radius of this smaller circle. Yeah, and this actually creates something that is, in my opinion, the most important collision detection formula in computer graphics. Because if you have two circles, okay, you have this formula, and you can discover then that d is less than 0. This means collision between the circles. Okay, if it is greater than 0, this means absolutely no collision. Why is this so important? Because of, exactly this, bounding circles and spheres. These images are breaking the copyright of Nintendo Corporation. And we have a Mario here and a mushroom. The point is that we can use something that is called a bounding circle on Mario and on mushroom. Bounding circle is usually the smallest circle that includes your sprite, your object. Okay, if it is a 3D object, the same thing you can do with a spherical 3D shape. All right. Of course, some objects will fit in nearly perfectly into a circle. Look at this mushroom here. It's nearly circular. Mario is not so circular, so there is plenty of empty space. But basically, this is some kind of estimation. All right. So what we do is we calculate the distance between the bounding circles, and if the distance between bounding circles is less than 0 or 0, then the collision is detected. An example is now. This will create a collision detection in this situation. This method of collision detection is not very precise, but it's very fast. It's the fastest. It's the best way to quickly estimate if we have a collision or not. Basically, the proper collision detection is a complex thing to do. For example, you started using GFC some time ago, so you should be familiar with a function known as heat test. The function heat test uses 3 different phases to detect collisions. The first phase is based on what you are looking at, okay, on a bounding circle. It just checks the distance. I may be lying actually, perhaps it just uses the second phase, but it could, okay? So I may be lying, but it doesn't really matter. The first estimation might be by bounding circles. Why? Because this is very, very fast. Why is it usable if it is not exactly 100% correct? For example, in this situation, our bounding circle based method will detect a collision, but you can see that there is no collision in fact. The collision is only between the mushroom and the empty space within Mario's bounding circle, so this is not a real collision. Okay, so this may be used as the first estimation. Please note that if this first estimation tells you no collision, so the collision test is negative, if bounding circles are not overlapping in any way, this is final. Okay, if bounding circle test says no collision, it means no collision. If bounding circle test says there is a collision, it doesn't mean that surely it is a collision. It signifies it indicates a possibility of a collision. So what we would normally do, the first test could be bounding circle. If it is failed, okay, if it is false, okay, negative test, this means no collision. End of the story, no collision. If the test is positive, you can go ahead and do more precise test, which may be, for example, based on rectangles, so-called bounding boxes. And this is, I think, what is currently used in GFC. Bounding boxes are just a little bit more complex to calculate than bounding bounding circles. Sorry. But also they are a little bit more precise. Again, same situation. If the bounding box test is negative, this means no collision, no possibility for any collision. If the test comes back positive, it only presents a possibility for a collision. Now, what to do in case of your collision test returns a possibility of collision? First thing can be, okay, my objects are small, fast moving. If a simple test says it's a collision, it's a collision. Hopefully, if there are a few missing pixels between two objects, my players will not notice anything. We can consider this a collision. That's the simplest option. Another option is to apply more specific, more proper collision detection method. One of these methods is a hierarchical approach to collision detection. I will go back to my Mario example, and I will show you that Mario could be estimated as a circle here, which will be a very precise measurement for a collision within his head. His main body could also be a circle, and we also have 4 rectangular shapes, okay, for both arms and legs. You could even add additional bounding circles here and here, so you can provide a number of bounding shapes, circles and spheres to increase precision. Quite interestingly, GFC is using a method which is basically pixel by pixel testing of overlapping between two sprites. It's very costly in terms of execution time. Therefore, it has to be controlled by the initial rectangle or bounding box test. Okay, so if the boxes, the sprites, rectangular shapes of the sprites do not overlap, there's no collision. If they do overlap, then very time-consuming but very precise test detection is applied with the method pixel by pixel, which is not covered in this lecture, by the way. But what is covered is the box bounding box method. So basically, if we have a rectangle and this rectangle can be defined by, let's say, upper left and lower right vertices, okay, or corners. But it is for collisions, it is better to represent a rectangle as a single coordinate xy with height and weight. Okay, so it's again a point which has a height and weight. I will go a little bit further. You are now familiar with object-oriented programming, so this notation should not be a surprise for me, but I will call my rectangle R, okay? So my x coordinate and y coordinate of the center of the rectangle are now r dot x, r dot y. The height is r dot h. The width is I wonder if I previously told you weight. Of course, I'm weight is 0 here, and it is wide. Okay, so it's with RW. Okay, so a condition for collision between, in this case, between a rectangle and a point, okay, is given by this formula. What is it? Px minus Rx. Px minus Rx, okay, this is the difference between the x coordinates of the point inside the center of the rectangle and the point we are checking. If this distance is less than half of the width, okay, this is half of the width, this distance here. So if the distance in x direction between these 2 points is less than r dot w divided by 2, this means a possibility for a collision, okay? But we also have to do the same calculation in the y direction. So in the y direction, this will be this distance. And looking at this picture, in the x direction, the distance between the points is wider than half of the width of the rectangle. So there's no collision in the x direction. There would be a possible collision in the y direction because the distance in the vertical distance between 2 points is smaller than half of the height of the rectangle. So we have a possible collision in the y direction and impossible collision in the x direction. Our condition for collision, however, contains the logical AND operator. So in order to see the collision, to detect the collision, it has to be detected in both directions, both x and y at the first place. Okay? One more thing, what this ABS is doing here. ABS is just the absolute value. So this is a function which returns the value of a positive number if it is a positive number, and still a positive value if it is a negative value. So basically absolute of 5 is 5, but absolute of negative 5 is also 5. Why we need this? Because we need the distance between these 2 points. Okay, I calculated by subtracting px minus rx. So in this case, the distance would be positive. But if my additional point is to the left from the rectangle, the result here would be a negative value, and negative value would always be less than r dot w divided by 2. So we need this absolute value to have the real distance between these 2 points. Basically, that's a solution for the problem of detecting the collision between a point and the rectangle. The next is a collision between the rectangle and the circle. Okay, and in this case, we add r, the radius of the circle, to both the width and height of the rectangle. So this formula only differs in this plus r thing. And just to show you that if we go here, the x direction distance between these 2 points will be slightly less than half of the width plus radius, okay, because they are partially overlapping. You could also consider that the collision between the rectangle and the circle is the same problem as a collision between a bigger rectangle and a point. Okay, so we can inflate the rectangle by the value of the radius. This is just to illustrate the idea that sometimes in mathematics there may be two different solutions for the same problem. Okay, they both lead to the same formula. Okay, there are absolutely an equivalent problems. This, what does ABS denote again? Kennedy, again, ABS denotes the absolute value. So distance for an object that is on the right is already positive. This calculation gives a positive value, so no problem. But if I moved the circle to the left of this image, px minus rx would produce a negative value, and ABS will convert it to a corresponding positive value. Turns negative numbers to positive and positive numbers to also positive. Yes, I read the chat. This formula, you have to be aware that there is a moment in which it won't exactly work. Okay, a small artifact is here. If your circle is exactly here at the corner of the rectangle, a small artifact will detect the collision whilst it is there is no collision. However, it's a very small mismatch, okay? And the way of calculation or solution for avoiding this situation is quite complex, so I will not complicate things by showing how to get it. Instead, we'll go to general condition for collision, okay? We have now two different rectangles with two different central points, Rx, Ry, and Sx, Sy, two different heights, Rh and Sh, two different widths, Rw and Sw. I should have drawn this second rectangle with a different proportions. I didn't think about it, sorry. And here it is. Here is the formula. Okay, we just have to take both widths and both heights together, and this will work for any two boxes. This method, this formula, is known as AABB, axis aligned bounding box. What it means, axis aligned, this means that your rectangles here are ideally horizontal or vertical, so both all four edges of both rectangles are parallel to either x or y coordinate in the coordinate system. There is a general solution for something like this, and it can be found in Canvas. If it cannot, I will add. Okay, but I wouldn't really like to make things totally complicated now by explaining how to solve this general case. I will just very briefly give you an idea it's all about rotations. Okay, so it can be reduced to the problem in which one of these rectangles is axis aligned, the other is not. There is a easy formula to find detect collisions between such two rectangles, and then you can just rotate these rectangles. But it's quite complex, so I wouldn't like to spend too much time on it. Particularly that we are now arriving to the second point today, what happens after the collision. But to find out what happens after the collision, and this is basically the answer is a reflection, okay? So mathematical model for bouncing. We will have a short break before continuing. So what happens after the collision, you will learn after a 10 minutes break. Welcome everyone after the break. I had some more tea, so I'm happy to continue. Okay, before we restart with the lecture session, I would just like to attract your attention to the new assignments that appeared in the assignment section. This is what you should by now see in your assignments in the module in Canvas. Canons, which were presented last week, and the deadline for submission of canons is 10th of February, and a new one, Bouncy Ball Physics Starter, which is due by 24th February, so in 3 weeks' time. Bouncy Ball has a proper discussion and explanation here, and also I have a presentable version of Bouncy project, which looks like this. So it should implement gravity, it should implement simple bouncing from the floor and side walls, and something that you have probably just noticed, if I click anywhere inside the window, there is a weak force attracting my ball towards the mouse pointer. Okay, so all the details you will find in Canvas. Also, method of submission. So it's important to notice there are 3 different methods of submission. You can submit in class. You must present your solution to the lecturer or tutor. You will receive feedback and get marked on the spot. You are still required to submit a screenshot of your game, not code, the game, okay, so how it looks like when running, to Canvas. The second possibility is source code submission, but because at least in these initial small exercises, you will typically just change mygame.cpp file, sometimes mygame.h file, then I would ask just to submit the files that you have modified to get things done. Okay. If you have more files than that, please zip them and submit a zip file. And the third method of submission, which is always recommended, and it will be obligatory by the time you achieve your final submission in this module, is a submission for GitLab. In case you prefer GitHub, that's absolutely fine. Okay, either GitLab or GitHub, basically a Git-based remote repository. So you need to export your project to the repository. Here is how to do it. Okay, it's a it's because yeah, you should be able to see this page. If you can't, let me know. And it explains step by step how to export a project using GitLab. I will not give you any instructions right now, firstly because it's displayed in this separate page. Secondly, because for now submission by GitLab is not yet obligatory. So if you don't know, if you can't do it, just give up and use any other method of submission. So this is about the current submissions. I also wanted to this kind of a demo program, which is slightly different from the bouncy ball, but also kind of similar. Okay, and the second part of the lecture will be based on this example and making it making it usable, making it working. So I have a green circular object, a ball, okay, and a floor. Okay, I probably also have. Oh, look, I can attract this ball to the mouse, but this is actually. It doesn't matter. Okay, that's not the thing that I wanted to show. The first modification we will do to this code is the same thing as we did last week with the cannons, and it is adding some gravity. I should have here. Okay, so we just accelerate the ball with the vector 0, -10. That's a pointing down vector, the gravity vector, and we should have yes, that's now the ball animated going down nicely. All right, so we have gravitation, but of course it's not fully nice solution yet, okay, because we don't detect collisions. So by now we know how to detect a collision. So if ball dot hit test a collision with the floor, that's the name of the other object. Well, exactly what to do. Let's for now ball set velocity to 0, 0. And let's have a look at it. Quite nice, right? So it drops to the floor, and we have a perfectly inelastic collision. Okay, no bouncing, but if it was a plasticine ball, it would be exactly this thing. And even I cannot. All right, so that's the first attempt. But what we really want to do is to analyze bouncing. So what I really want to do today is to get reflections, so mathematical model for bouncing. We want this ball to bounce off the floor and jump several times. Okay, the basic model might look like this. So we have something. Okay, this something is not shown here, but we have a vector of velocity pointing towards a wall in this case. Sorry. So that's the velocity, and after bouncing from a wall, we will have the final velocity. That's the final velocity, and the final velocity, if the velocity before reflection was xy, then the velocity after reflection, after the collision, will be negative xy. Negative xy. This is that simple, okay? Why it is negative? Because this is a symmetrical action, symmetrical phenomenon. Okay, with disregard now to something that's called restitution, which we'll discuss later today. The speed towards the wall is exactly the same as speed outward speed, so away from the wall. I'm just realizing that I didn't see the chat. Okay, it's back with me. All right. So that's a before and after situation. But there is one reason why I'm very deeply unhappy with this diagram here. Why I'm so deeply unhappy with this diagram, so unhappy that I will present it in this way. Basically, in physics, vector diagrams always show vectors originating from the position of the object we are interested in. If you look at this picture, we would have the initial velocity of something that is here in midair at some distance from the wall, and then the final velocity is indeed of something that is in contact, in collision with the wall. So instead of this diagram, I will much more prefer this one, which maybe is a little bit less intuitive, but it's mathematically and physically precise. So at the moment of the collision, and we will be interested at the part of the object that really is colliding the wall, okay? At the moment of the collision, the velocity of the object is given by this vector, and please note that if there were no wall, this object would continue its movement along this vector. But now, instead, it will bounce off and get this vector v prime or v final. And this is what we call reflection. If you look at it, it's ideally symmetric and it looks like a reflection in a mirror. Okay, this is why it's called reflection. So this was a special case of reflection from a vertical wall. It won't help. It won't help in our example because our ball should be bouncing off the horizontal floor. So let's rotate it. We still have velocity pointing down and final velocity pointing up. Our velocity in the program example, of course, it is pointing directly down, so it's strictly vertical, but it doesn't matter. The general formula is here. If my initial velocity is xy, my after velocity, so final velocity, will be x negative y. And this gives me something. I could tell something like this. In the case of heat, instead of setting the velocity to 0, I could set the y velocity. I have special functions in GFC which only affect x or y component of the velocity. So I could use one of them, set y velocity to value of get y velocity. So that's get y velocity is the initial y component of the velocity, and by adding a minus by adding a minus here, I should be able to model the velocity bounced from the floor. So let's test it. Sorry, I have to switch my program first. Yes, it's bouncing. It's bouncing higher and higher, but we don't. The fact that it is each time bouncing a little bit higher, it's just small imperfections in calculations, and we will get rid of them very, very soon. So don't be specially bothered by this. But we have a general bouncing movement. I will propose a little bit more elegant and flexible notation. So after setting up the gravitational pull, I will do another thing. I will create a C vector, which I will call V, and this V vector will contain the velocity of my ball, okay? Of the ball, it's a unlucky, not a very good name. It should be marble, okay? Of the ball. You know what I mean. Anyway, get velocity. All right. And now, here, I will just tell that y component, the y component of my velocity becomes negative y component of my velocity. And here, just before the update, I will just call one more function of the ball. Set velocity v. Okay, not that this code would be drastically better than the previous version, but it is more flexible and it is easier to modify in the proper way. All right, so let's. So no change here. It behaves exactly as it did previously. Please note that because I have this power to attract my object, my sprite, towards the mouse cursor, I will try to do it and make this bouncing movement a little bit more interesting. Okay, so you can see that it's working quite well. All right, but in gaming, floors and walls are quite popular things, but quite often we will have a situation like this, a diagonal object, a diagonal wall, whatever. So we would really want to find a generic formula for movement of an object after reflecting from a surface. If we know the surface, and the surface doesn't have to be horizontal or vertical. Okay, so how do we know what is the final velocity? Because it's still a reflection. It is still something that is symmetric across the borderline between the object and the exterior of this object. So this dashed line here will always be perpendicular to the surface of the wall. Okay, and the popular way, the main way, the most important way of precising, of indicating direction of the surfaces in 3D graphics is for defining the normal vector. And you should know by now what is a normal vector. A normal vector is first of all a normalized vector, and it's perpendicular to any kind of a surface. Okay, perpendicular to a surface. So what we can do now, if we know the normal vector to the surface, please remember it has to be perpendicular. Okay, it has to be magnitude 1. Then we can do a simple mathematical modification. I can draw my n vector here, and if you remember anything from dot product, then you should be able to find out this distance here. Okay, you remember in the first test you attempted in December, you had to solve a triangle using vector algebra, and this was using dot products. Basically, if you have a situation that you have this triangular situation, and it's important that this is a right angle here. You can find this length here using the dot product of v dot n. It's important that n is normalized. Okay, it shows the direction, and the whole thing is called a projection of a vector v to the direction provided by n. It's also important that usually we have vectors starting at this place and pointing towards this direction, determining the hypotenuse of our triangle. In this case, we need to take negative v because v has quite a strange pointing, okay, direction. But this means that we can determine the value of this green vector. The green vector is projection of negative v towards the direction of n. And according to one of the formulas that you learned in December, this value is negative v dot n times n. Okay, v dot n is a number. It's the length of this edge in the triangle. So if in case you remember, and if you don't, maybe it's time to refresh your knowledge to find the adjacent and the opposite side of a triangle without using trigonometry but using vectors. And if you know the vector built on the hypotenuse of this triangle, then you have the adjacent side is v dot n and the opposite side is v cross n. We are not using cross vectors, cross value today. We will be using cross next week because that's quite a fundamental thing in 3D, 2D and 3D geometry. But today it's just dot product, and dot product gives you the length of this edge. And we first of all take a negative because we need to invert this vector v, and we multiply the length of this edge by the vector n to convert a number. Remember, v dot n is a number, to convert this number into a vector. So the green vector is negative v dot n times n. Because this is a reflection, so we can be sure that this vector built on the other side, another green vector, will be also negative v dot n times n. And this means that we can now find the geometrical solution of our problem. V prime, or v final velocity, is equal to the initial velocity v minus v dot nn minus v dot nn, or v minus 2v dot n times n. Okay, that's geometry. This vector plus this vector plus this vector, so gives us this formula. This is quite a fundamental formula. This formula is known as the reflection vector. Okay, and basically it is used to find the final velocity of an object, okay, after bouncing from any surface. Okay, so this is your initial velocity, this is the normal of the surface, and this is the final velocity. Okay, final velocity can be obtained from this formula. Let's apply it to our code. So it will go here, and I will just say v equals surprise. This is such a fundamental function that CFC has this function built in. Okay, reflect Vn. V is our velocity vector, and should be the normal of the wall. Okay, and this will calculate the final velocity of the ball. We are missing n. Okay, I have to comment out this function just in order to compile. Okay, we are interested in this floor here. Okay, normal for this floor is a vertical vector pointing up with a magnitude of 1. So x coordinate will be 0. Oh, the ball has just flown across this the screen. So x coordinate is equal to 0 because this is a vertical vector, and the y coordinate will be equal to 1 because it's pointing up. Okay, not down, it's pointing up. It's always pointing outside of the surface. So what I am going to do is just to add c vector n equals c vector 0, 1. And we will see if the reflect function, which I now have here, uncommented, it works perfectly. It works perfectly. Back to the presentation though. This was the ideal situation, okay? Ideal situation is with the velocity pointing towards the center of the wall, okay, inside the wall. This means that the object is just bouncing off the wall. It has its velocity pointing towards the wall, and now it goes. It is going to go out to go outside of this wall or away from the wall. Okay. But in real world, it would work like this. In digital simulation, quite often we will have a situation like this. What that means? We have a vector of velocity already pointing away from the wall. And in this case, we don't want any collision. And I will show you an example. I will try to show you a glitch. But to show you a glitch, I first of all will resolve another glitch. And this another glitch is something I already showed you. Okay. It's bouncing. Look, every time it bounces from the floor, it goes a little bit higher and higher and higher. And we all know that in the real world, it would never happen like this. In the real world, it would always, after bouncing, it would slow down a little bit. So what we can do, the value of reflect function is a vector, the final velocity after reflection. If I just multiply it by some number, 0.9 for example, multiplying a vector by a number is so-called scaling. Multiplying this vector by a number which is slightly smaller than 1 will make this vector a little bit smaller, okay? So it won't change its direction, it will change its speed a little bit. Let's give it a try. Okay, and this works perfectly nice. With each bounce, it's going lower and lower. And this coefficient 0.99 even has its physical name, which you might recognize because, sorry, it was mentioned in our lectures at least twice, okay? And it's called restitution coefficient, coefficient of restitution. I will make it quite strong now. Okay, did you see this? After 2 bounces, it looks stuck to the floor. Try again. Should normally bounce several times, but now it's stuck. Okay, something strange happens because from time to time our marble gets stuck in the object from which it should bounce off. And the reason for that is the exact situation I showed you here, that the reflection formula is applied in the moment when the ball is already flying away from the window. You could ask, okay, what happens? It shouldn't, okay, because after all, this ball is flying towards the floor, bouncing off the floor, and that's it. The problem is with something that is called interpenetration. Another funny name, but this is how it's called. I'm loading a second set of slides. Just a moment. Okay, object interpenetration. In the real world, if I have a marble and some object, let's call it a floor, okay, in the real world, it's just falling down and bouncing, okay? In the simulated world, however, it is something slightly different. Okay, in the simulated world, we have frames. Frame 1, frame 2, frame 3, frame 4, okay? And the problem of object interpenetration is that as a result of limitation of animation frame rate, collisions are only checked every frame, and we have no guarantee that our collision will be detected at the moment in which the object is really touching or starting at the collision situation. So quite often our objects will overlap first, and only after they are overlapped we will detect the collision. It's not the problem of a mathematical model of collision detection, it's the model of animation frames. Okay, we only have control over our objects 60 times per second, and if an object is moving reasonably fast, it may happen that it will overlap another object before we detect the collision. Possible solutions, zero solution, maybe surprisingly good practice for small objects. It's just you do nothing, you hope that your players will not notice. You can move object to the contact position. This is done each time when the collision is detected, but the visual effect may be hardly better than the zero solution. You can increase the frame rate, but this may be costly and still not fully effective. You can only increase update rate. Sorry. So you can do several updates per each rendered frame with shorter time deltas. Also quite costly and also not 100% effective. And you can also try to calculate the exact impact time. Okay, so there are some solutions. Basically, why we worry about object penetration. Object interpenetration may cause unrealistic visual effects, but with small object in fast motion, this may be barely visible. But also, object interpenetration may distort collision response algorithm, and I'm explaining how. In the real world, before we have an object just above the floor, then it's hitting the floor, then it's going back upwards. Let's add velocity vectors, okay? So in the situation below, it's moving downwards, the green velocity vector. At the moment of the hit, it's still pointing down, but bouncing off will create the velocity which is upwards, and it will continue to fly upwards with a little bit smaller motion when it is above the wall. Of course, this velocity will be gradually decelerated by the gravity. So this is the real world, and This is the same situation in the simulated world, so with the object interpenetration. This is before the collision, this is during the collision, okay, the new force after the collision, and it's flying up, and there's no problem if this looks like this. Now, why the glitch we had occurred more often with lower values of restitution? It's simply because with restitution, this blue velocity is smaller. Okay, it's after the collision, it's going slower. Okay, and therefore it may happen that the situation will be like this. If the final frame before the collision catches the object just above, it's still no collision, so the guy is flying down. Okay, then the next frame is already overlapping the floor quite significantly. We don't worry about it. We just reverse the velocity upwards, okay, and make it fly away from the wall. But sometimes it will happen that the next frame will see the ball still touching the floor. It will be a little bit higher than the previous frame, but it's still touching. Okay, so what we do, we have a heat test. Okay, remember the code. We have the heat test, so we apply reflection formula, and we get movement towards the wall. It's apparently wrong, okay? And this is exactly what happened. This is the glitch we have with object interpenetration. Sorry. What we can do, this is a general solution. A ball is flying happily towards an obstacle. Here is the normal vector of this obstacle, okay? And for the ball to happily bounce off, these two vectors have to point in two opposite directions. Opposite directions can be detected by dot product. If v dot n, velocity dot normal, is less than 0, we can apply bouncing without any danger of doing anything wrong. But if v dot n is positive, this will mean that the object is already bounced, okay, has already bounced off the surface, and we should give up with any further attempts to reflect this velocity. So I will add additional condition here, dot vn. So this is a standard GFC function to find the dot product of v and n. So it's v dot n, and it has to be less than 0. With this addition, we don't have our glitch anymore. Okay. All right, I will check because I lost the view of the chat, but there's nothing new in the chat. So going back to the main presentation. So we definitely want to avoid using this formula in a situation like this, with the velocity already pointing away from the obstacle, okay? So we have to remember that there is no collision if v dot n is greater or equal to 0, okay? This means that The velocity is already in the direction of the normal, so it's already moving away from the wall. So let's modify. Let's modify our formula here. Final V is V minus V 2 V dot n, and only applicable if V dot n is less than 0. This is nearly the end of this session. Okay, take home messages. Collisions can be detected using bounding circles or spheres or bounding boxes, and you now know how. And if you detect the collision, you should implement the collision response, and collision response is mostly based on the reflection. Reflection multiplied, of course, by restitution coefficient. Okay, the formula for the reflection is provided here. If you are using GFC, this formula is easier for you to use because there is a built-in function called reflect, which will provide calculation for you automatically. But you should always remember that this formula is only applicable when V dot n is less than 0. One more final thing. I don't want you to necessarily go through all these maths unless you wish to do so. But just to show you that this formula is really working also for our standard collisions. Okay, so this is the collision against a vertical wall. If this is a vertical wall, then the normal vector is -1, 0, pointing leftwards. So V is x, y, n is -1, 0. Formula is like this. Okay, doing all the calculations, which I will not follow here, but you could, all right, and I will recommend to do it before the test, which will be after reading week. Okay, so we may revisit this example next week. But if you do all your calculations, you will find out negative x and y is the solution for this case, and x negative y is the solution for this case. All right. So there's absolutely no reason why not to use these simplified formulas with just negative x or negative y if you know that your wall is either horizontal or vertical. Okay, but still a full reflection formula is very useful in situations like this one. Okay, so here we have a diagonal obstacle. Okay, diagonal obstacle and a realistic bouncing off. Okay, but to find the reflected final velocity, you need to use the normal vector of this surface, which will be pointing more or less this direction, and you also have to apply the reflect functions. But for today, that's all. That's everything. I will get back to this example next week because the topic for the next week are implementation remarks in collision detection and response. Okay, so the next week session will start with the physics test, of course. I have your test paper already on my desk. I will not show it to you. It was prepared ready for today, but it will be used next week. So I invite you for the test next week and for quite an exciting session about implementing various types of collisions. My final remark is about the bouncy ball activity, or second small programming activity due later in February, in 3 weeks time from today. The basic solution looks like this, and if you implement all the aspects that are requested and required, you get minus A, okay, 70. So it's a first class mark, but no extras. Okay, to get extras, so what I mean as extras, it's a better mark than A minus. I would expect at least something like that. Okay. You could also have a circular object from which you could bounce your marble, or even have several marbles on in the same window. But this extensions of the collision technique will be discussed next week. For now, I thank you very much for participating in this session. Okay, I survived. I'm still alive. We started late and we finish early, but that's the logic of a remote session with a lecturer with flu. Okay, so I hope to be fully recovered by next week, and it will be a great pleasure to see you again in the class. Thank you, and see you next week. Okay, that's a